Section 11.6 is all about solving nonlinear systems of equations. So what you're going to be doing is pulling together basically everything you already know about systems and everything else you know about all the different functions that we've studied so far in order to solve these systems. The very first problem that you see here is one that you probably saw last year in 90s, where you have a parabola intersecting a line. Now I am providing you with a graph for each one of these questions just so that you can kind of reference and have a way to check your understanding, but it's not going to be given to you every single time, especially not in your homework and especially not on the test. So you need to be able to algebraically calculate something and know that it's correct without relying on a graph. But this is just to kind of reinforce some concepts. So I do have a graph provided for these examples. All right, now when you see this first example here of this quadratic here intersecting with this line, you can use a couple different methods. You could use elimination here. If I was going to use elimination, I would have wanted to eliminate the y's because I cannot eliminate the x's. So I'd try to eliminate the y's. In this case, though, I think it's probably easier just to use regular substitution. So I am going to let y equal negative x squared plus 5. And then I'm going to take this term and substitute that in here for the y. So this is just like a normal substitution question where you have negative 2x plus 3 times negative x squared plus 5 equaling negative 6. And now I have negative 2x, well, let's just simplify this. So negative 3x squared minus 2x, adding the 6 over here to the 15, I'll get positive 21 equals 0. Now this problem is actually factorable after I take out that negative 3, or that negative here. It might be a little bit easier for you to see what these factors are going to be. So this is going to factor into 3x, sorry, the negative sign's out in front still, minus 7, so 3x minus 7 times x plus 3. Okay, so that means I have two solutions here for the x, positive 7/3 and negative 3. Now, you can clearly see that this is intersecting at two different locations here, but the reason why we are also seeing that is we have two different x values here, and we can plug that in to solve for our unique y value. So if x is equal to 7/3, then your y variable is going to be this term squared plus 5. So negative 49 ninths plus 45 ninths gives me negative 4 ninths. And for the x equaling negative 3, a little bit easier to calculate, but that's just the opposite of negative 3 squared, so opposite of negative 9 plus 5. So y would equal negative 4. So when we list our coordinates, make sure that you're listing them, not just solving for the y and the x, but actually listing them as two coordinates, because that's what our whole point of this problem is to figure out where they intersect. So it would be negative 3, negative 4, and 7/3, negative 4 ninths. Okay, these are our two unique points where those two intersect. All right, so let's do some more examples. These are all different from one another, and they are unique, and that's why the book, actually, these are straight from the textbook. The book is using these ones as your examples for the rest of your homework. So you're more than welcome to try these questions before I start on them, but if you run into any type of misunderstanding, make sure you watch the full video, okay? All right, and problem 2, the reason why this one is here is, one, I think that you're probably going to want to substitute x squared in for the y. And not that you can't do that, but you're going to end up with something that turns into an x to the 4th. And you could factor that all you want, that's fine. But I'm going to use elimination here, because I think sometimes it's hard for you to see why you can use elimination. So if I were to subtract that x squared over to the other side, I now have this equation here. And I can eliminate the x squareds, leaving me with just one variable here. So I have y squared plus y equals 1. When I add these two equations here together, I end up with y squared plus y equals 1. Now I just have a quadratic where I'm going to solve for the y. So after I use the quadratic formula here to solve, I end up with y equaling negative 1 plus or minus root 5 over 2. Now, negative 1 plus root 5 over 2, this is going to be a positive value, and negative 1 minus root 5 over 2 is a negative number. Okay, so this is a negative. And if you look in your original equations here, Your y output cannot be negative here for any value of x. You plug in anything and you square that, your y output will always be positive. So that means that this solution here, this y equal to this negative number, you can't use that. It's not going to intersect. So what we end up with here, once I take this y value, so if I let y equal -1 plus root 5 over 2, and I solve for the x here. So if I were to solve for x, in this case I would have x equaling positive or negative root y. Okay, so I'm going to use this y, plug it in here so that I get two unique solutions for the y, or I'm sorry, for the x, positive or negative square root -1 plus root 5 over 2. So there are two unique x values and only one y output. That's the positive here. So when I write my coordinates, I have positive square root of -1 plus root 5 over 2, comma, the y variable, which was just the positive value here, -1 plus root 5 over 2. And the other coordinate would be a negative square root of -1 plus root 5 over 2. And the y value is still the same, negative root 5, or -1 plus root 5 over 2. So you can see this graphically, and I think it makes more sense when you see this graphically, but you won't be able to see a graph necessarily unless you were to use your calculator, to check your answers. You would have to be able to pick this up while you're solving through this algebraically. And the reason why we have to throw this out, we do not get 4, otherwise we would get 4 unique points. We throw out that negative again because it doesn't work for this equation here. The output for this x squared, and whenever you put an x value in here, the y must be positive, so we can toss out that negative value. And you can see it graphically that it's only crossing at these two coordinates here, and these would be our 2 points. Alright, so that's the exact answer for both of those intersections. Alright, moving on to problem 3. You can see here that in problem 3 there is no intersection of this circle and that square root of x. So I want to just show you what you would see algebraically to let you know that there is no solution for this. So in this case, probably the easiest thing to do is just plug in root x right in for y here. So I have x plus 2 squared plus x equals 1. And now I have it in in terms of one variable, so I have x squared plus, after I FOIL this out and combine like terms, 5x plus 3 equal to 0. So I'm going to use the quadratic formula now. Okay, so after using the quadratic formula, I end up with x equaling two unique solutions here, a -5 plus or minus root 13 over 2. Now, coming back to that same kind of idea that we just saw in the last problem, if you look at your original equation here, y equals the square root of x, we know that x has to be greater than 0. This must be a positive value in order to, or sorry, greater than or equal to 0, I should say. So positive or 0 must be the input for the x value. So right away you can toss out that -5 minus root 13 over 2 because you know that this is clearly a negative number. Now the other one is not so obvious. -5 plus root, -5 plus root 13 over 2 is also going to be a negative number because this is not larger than 5. So it's obviously between 3 and 4, which is why this is going to result still in a number that is also negative. So we can toss that out. And again, it's because it doesn't fit inside this equation. You cannot have your input here be a negative number, which means that there is no real value. If you were to try to solve for y here, you would plug in a negative number here, which is why you end up with a non-real y value. So that means that there is no real solution for this because there is no intersection. And you can clearly see that with our graph. But again, you would not be provided with the graph. You'd have to be able to pick that up algebraically as you're solving through this. So you constantly need to check whether or not it fits within your, your original constraints, those equations that you're given. Okay, now problem number 4, you have two exponential equations here and you're finding the intersection. So I've got it clearly graphed here. You're going to see that you only have one intersection here. So algebraically, the solution for this, now that you have like a certain technique down, it should be pretty easy for you to pick up on how you can use substitution here. So I know that if y equals 3 to the x, I can use this to and substitute that into the other equation here, but I need to rewrite this so that I'm able to do that substitution. So I'm going to rewrite that second line as 3 to the x squared instead of 3 to the 2x minus 2. Okay, now this can be substituted in. Remember, 3 to the x is the same as y. Now I have y equals y squared, right? I'm just substituting in y equals 3 to the x minus 2, and now I have an equation in one variable. So I have a quadratic here that I'm going to solve. So y squared minus y minus 2 equals 0. And luckily this one is factorable, so y minus 2 times y plus 1 should equal 0. Y will equal 2, and y will equal negative 1. Now we have to go back again and check to see whether these solutions, because this is showing two distinct y outputs here, and obviously from our graph we're only seeing one, so we only should have one intersection. Now again, you won't be given this graph, you'll have to be able to discern this for yourself by just solving algebraically. So when you take a look at your y outputs here, y equals 2 and y equals negative 1, let's say you wanted to plug in y equal to negative 1 here. You should know, because we already know that our exponential function y equals 3 to the x, we've studied exponential functions a lot, we know that the outputs here must be greater than 0. Okay, this function will never be a negative value. It approaches 0, but it doesn't become 0, so we know that negative 1 can be tossed out. So what we're left with then is that if y equals 2, then you have the equation 2 equals 3 to the x. Now if you want to solve for x, we can use our definition of a log or just take the log base 3 on both sides, but we end up with log base 3 of 2 equaling x. So our intersection then is the coordinate log base 3 of 2, comma 2. So that would be the algebraic intersection, or I'm sorry, the intersection found algebraically for this system of equations. Okay, last up we have problem 5. Problem 5 should look similar to a problem that you saw already in section 11.1. So the setup here is going to be very similar. This is the same technique that we used before, where we're going to say let a equal 1 over x squared, and let's let b equal 1 over y squared. This is going to change this system from a very complex, system into a linear system, a really basic linear system. So you can, choose any variable you want here. You don't have to use a and b. I just really like to use a and b. So anyway, I'm left with 2a minus 3b equaling negative 6, and 3a plus 4b equaling 59. Now I have a system here that I'm going to solve. Alright, to save some time, I solved already this system, so I end up with a equals 9 and b equals 8. Now from here is the important part for how you're going to actually solve for x and for y. Now you're going to use substitution back in here. I'm going to since I let a equal 1 over x squared, I'm going to now replace that with 1 over x squared. And I'm going to replace the b here with 1 over y squared. Okay, so I'm just retaking that and using this idea here and here to use substitution again. So now I know that x squared should equal 1/9 and y squared should equal 1/8. So to solve from here, taking the square root, I get x equaling positive or negative square root of 1/9, which is just going to be 1/3. And over here, y is going to equal the square root of positive or negative square root of 1/8. And in this case, I do need to reduce, so I have positive or negative 1 over 2 root 2. And we're not going to make you rationalize the denominator here, so you can leave that radical in the denominator. So I end up with 2 values for x, 2 values for y. Okay. When you write this coordinate, make sure you understand you have 4 unique coordinates. One is going to be with positive 1/3 and positive 1 over 2 root 2. The other one is going to be with positive 1/3 and negative 1 over 2 root 2. And you will also have a negative 1/3 with a positive 1 over 2 root 2, and negative 1/3 over, negative 1 over 2 root 2. And these are your 4 unique coordinates where these equations here will intersect. All right, that's the end of the lesson. I will see you in class mañana.